Hello, my name is Richard Warburton. I'm from Opsian, and we're a company that does continuous profiling tools. This talk is called Continuous Profiling Production, What, Why, and How. It's not really a talk about tools itself or about our product in particular. It covers a few different topics. So firstly, I'm going to talk about why performance tools matter and what kind of methodology is here which performance tools fit into. Then we're going to talk about the distinction between development and production environments and why specifically, from a performance point of view, you want to measure things in production rather than from development. Then we're going to look at the distinction between profiling tools, monitoring tools. How can you get that data back from production that's accurate, high quality, and helps you solve problems? And then we're going to conclude this talk and wrap up the different threads we've encountered. So firstly, when we're thinking about problems in terms of software development, we can kind of think of three different categories of problems. Firstly, there's your known knowns. So these are problems where you know they're a problem and you know the kind of specifics around it. So for example, we know that reading data out of RAM is faster than a hard disk. We know algorithmic complexity, basics of architecture and design. These are things that allow us to reason about our code before we even run it, a priori, ahead of time. And that means that we can understand some of the performance characteristics of our known areas of our application ahead of time. Then there are your known unknowns. So when you start to take a design and put it into production, what are the series of known unknowns that you have? So for example, you might have a remote service call to another service. How long does that take? You might know that RAM is faster than hard disk for reading data, but you don't really know what the ratios there are on your specific production system. You don't know how long queues end up in production, but you know you might have a queue between two components, and it would be bad if that queue is forever growing without bounds. So these are things where you can reason about them, but you don't know the specific answer ahead of time. And tools can help you measure what those problems are. Then we get to our unknown unknowns. These are things where you don't really know the production characteristics ahead of time, and you hadn't actually thought that they even could be a problem. Maybe in practice, you find that these are all problems that you could have thought about ahead of time, but you just didn't happen to. That's often the case. We can't get everything right ahead of time. We can't know everything up front. It might be, for example, you've designed some beautiful, clever parallel algorithm, but the performance of that is constrained by your logging framework having a big lock in the middle of it. It might be that actually the characteristics of users using your site are completely different from what you thought of ahead of time, and the performance problems are all in a different component to the one that you performance tested and optimized heavily before launch. These are your unknown unknowns, and these are the things where you really would have difficulty understanding them without measuring the production performance of your system. Then there's a distinction between development and production environments. So when we write software, we often write it with a bunch of development environments in mind. That's your laptop, your IDE, all sorts of things like that. And when you do functional testing of software, we do it in a development environment, right? You can run JUnit tests, you can run system tests, you can do all sorts of things like that. They test the functionality of your software very effectively. And, you know, that's cool from a functional point of view. But performance testing and performance assessment in a development environment is very, very challenging. We're going to look at the different reasons why and why measurement approaches that work in a development environment don't work in a production environment aren't really that helpful for you. Production is the real world. Production is where your users are, where the money's made. It's the important area where your code runs. So firstly, unrepresentative hardware. Look, developer machines can often get very beefy performance-wise these days, but they're often still quite different from server class machines. No, so you might be using a laptop to develop on, which has a few very fast cores, versus a server that might actually have slower clock speeds than your laptop, but might have, say, a bigger CPU cache or more cores. Now, you might think, look, Richard, if my code performs okay on my laptop, why wouldn't it perform okay on a server? And the answer is that you often get problems in different areas of your code base. A laptop with a few cores might have difficulty finding a lock contention problem that might become very, very visible on a high core count server that is unable to use all of its cores effectively. It might also be the case that nowadays you deploy onto very small AWS instances, like micro instances, small instances, lots of little instances there, and those machines can sometimes be much slower than your developer machine. So it's not always the case that your development machine is faster these days. Again, the distinction in ratio between CPU speed and disk speed, or CPU speed and, say, a Postgres instance running on the same box versus a production system where it might be running on a different box entirely. These are things where, you know, the hardware pushes the performance to a different area, to a CPU bottleneck problem or a disk I/O bottleneck problem. Then there's unrepresentative software. Here's a graph of different Linux distros and how they've evolved over time. We talk about things like Linux as though it's one thing. It's actually a variety of different distros, and that's not even the main problem. The main problem is that people use things like Mac OS and Windows in the development environment and then go and use Linux in production. Now, I'm not saying that you should throw away your beautiful MacBook in favor of a different piece of hardware or a different software setup. I'm just saying you need to be aware of these differences. The scheduler within the operating system will be different. The network stack will be different. These are things that affect server-side software developers quite a bit. Not only do you have the operating system distinction, but you have different versions of things like libc, you have different versions of things like the JVM itself that can perform very differently or have certain pathologies. Not only that, but you might have the same operating system with a different version and have a different performance characteristic within that. So Windows 10, for example, had a 40% drop in UDP throughput from a Patch Tuesday update in the first week of May 2018. That's a huge drop in speed if you're using UDP, a big challenge. So different versions really matter here, and making sure that either you're running the exact same setup in development and production, or that you are aware that this is a distinction that you have between your development environment and production environment is very, very important. Then there's the unrepresentative workload. If you're going to understand a performance problem, you need to have a way of reproducing and testing that performance problem. Okay, so you need to have some performance test, some workload. There are different names for this concept, and those workloads, performance tests, need to be similar to what your production system is doing, ideally identical. And differences between those workloads can result in different behaviors within your application. So it might be the case that your performance test runs with one user and your production system runs with many users. It might be that your performance test has a different distribution of requests across endpoints, like maybe it hits one endpoint a lot repeatedly and then moves another one, and your production system sort of flitters with an even load between different endpoints, different web pages that you have to hit or have to load. And that can affect, for example, the difference in caching, the difference in distribution between hot data and cold data, and then there's the concurrency and independence with requests. If you've only got one user hitting lots of different requests at the same time, you might well see, for example, a lock around some part of that user's data becomes quite hot. But maybe in a production system where a user just browses to one page at a time, different users hit different parts of the data, it might not be a problem. So you can also get situations here where maybe you spend time optimizing things that aren't real production issues, as well as not finding the production issues that are important to you and your organization. Also, the JVM itself may have very different behavior in production to your system. Sorry, may have very different behavior in production to a development environment. So why would that happen? Well, The hotspot JDK does adaptive optimization, so it kind of warms itself up when it first starts up, and it sees and measures what methods within an application are being called and what paths are hot, and then it optimizes and JIT compiles things that are hot and inlines things based upon a hotness threshold. So hot here means gets called a lot, gets used a lot. In certain situations, you might find that Hotspot has a different paths that it feels are hot under your development environment, under a different workload to a production system. Another example that you can see here, for example, is clusters. Sometimes, and I've seen experience of this myself before, where you have a cluster with a strong leadership algorithm and some followers. And when the leader was executing the business logic, it warmed up and sped up all of those paths. And then when you had a net split and there was a failover election from a leader to a follower, so a different system became the new primary, the new leader of the cluster, that new machine would be in a situation where it had a bunch of cold paths in its code, where Hotspot had adapted into a situation where all these things that weren't being called before were suddenly now being called, and you would see a throughput drop off immediately when you did that failover from the old leader to the new leader, and it eventually, in the case that I saw, eventually adapted back up to similar performance level, but you would get a big throughput drop immediately. And you can sometimes see that in development versus production environment as well, where you have different paths that are hot in development and different paths that are hot in production, and when things like this happen, you get a different output, a different performance characteristic. Okay, ultimately, I have no idea what I'm doing. To an extent, you have to accept that this is the truth, right? Like the dog looks cool, but you don't want to be this dog. You don't want to be pretending that you know what's going on when you don't necessarily know what's going on. Development environments will not tell you what exactly, precisely, accurately is going on in a production environment. Measuring them can give you false indicators, and what you really want to do is measure what's really going on in the real production environment and get the right answers, accurate answers. Okay, so the first thing you want to think about then is, if development is not an okay place to measure performance, what can we measure in production? How do we understand the performance of our production system? We don't have a debugger, we don't have an IDE. What's the data that we can exfiltrate from there effectively to understand the problem? And the first thing we encounter is metrics. You can call them ambient, passive, or system metrics. These are basically pre-configured numerical measures, so they are numbers that tick over a certain time period. You can store them in a time series database. You can query and aggregate over them. Very, very nice and simple. There's lots of code out there that will do this. An example of the kind of metric we might see, CPU time usage, or you might get histograms of things like page load times over time. Lots of example metrics, lots of things people out there. Metrics are really good because firstly, they're really cheap. So by cheap, I mean they're very low overhead for measuring what is actually going on in your production system. And they can often be very effective for narrowing down big picture performance problems and big picture issues. Sometimes you can just look at metrics and see and solve the problem outright, not always, and that's where the problem lies. Metrics can sometimes turn into one of these murder mystery style weekends. You know what it's like. The end of one of those Hercule Poirot novels where you get to the end, Poirot gets everyone down in a room, he points to the people one after another and says, "You were the murderer." "Oh no, it wasn't you." "You were the murderer." "Oh no, it wasn't you." And finally, the final person that Poirot gets to, they were the murderer. Always happens that way around. And sometimes that can be the case when you're looking at metrics. You want to try and find something that's unusual, out of band, and it can take you a while if you're looking at these things manually rather than having something automated to point them out to you, that it can take a while to find metrics that are problematic and understand what the root cause is from that. Even when you've got the metrics that are out of line, often don't give you a vector into your code base. They don't tell you where in your system you need to change things, where you need to fix things. So logging is another thing that we can use in order to help narrow down these problems. Now, I've put logging on one slide here, but it's really kind of two distinct things. Firstly, there's arbitrary events that you as an application developer have written to improve the observability of your system. So it might be things that you punt out through log4j or SLF4j. It might be more complicated logging systems. Some people have got monitoring and observability tools that are focused on event-based data sources as well. Now, application level logging of events can be very useful, can be very detailed, but the downside is that you have to manually add those things, and they're always very a priori in nature, right? They're always things where you have to have added something logging an event beforehand in order to see what's actually going on. Then there are also other types of logs from different subsystems within your machine. So it could be things like database Postgres logs. It could be things like GC event logs. Those are all very, very useful sources of data, but they are usually only useful when looking at that subcomponent within the system. So logs can be useful, but they can be time consuming to add if you're talking about human ones. They can be expensive to collect because you're often ingesting large quantities of text-based data, and they can, in the case of things like GC logs and Postgres logs, be kind of specific to a certain subcomponent within your system. Then there's coarse-grained instrumentation. So this is the approach that gets used by most application performance monitoring tools that you see out there. So instrumentation is basically the act of taking some extra code and adding it in, or instrumenting your application code with this extra code. And that can be used to measure properties of the code being instrumented. So you can measure the time within that code. So for example, take the time at the beginning of a method, at the end of a method, subtract one from the other, you know how long that method took. And this is a very useful approach for things like how long did we spend inside the controller layer of the web app rather than talking to the database, or how long did we spend performing a certain SQL query. Very detailed, potentially very actionable, although also quite expensive to collect. The problems with metrics with instrumentation are essentially that it has overhead, and the more detailed your instrumentation is, the more overhead your system has. And the other problem that you get with instrumentation is you have to have, again, added that instrumentation a priori. Those certain tools will automatically do that for you, but they have to have thought of the problem a priori themselves. We'll see an example of where that goes wrong in a little bit. Finally, there is production profiling. So profiling is a very general methodology about saying what was the dominant consumer of a given resource. So what methods used up CPU time? What lines of code allocated the most objects? Where did CPU cache misses come from? Profiling is automatic, so once you've got a profile that worked for a JVM application, it'll work for any JVM application. It's not like you need to do something specific to adapt it to your code or instrument your code or do specific coding for it. It'll just work out the box. Big win. Profiling can also be very cheap, i.e. very, very low overhead, but it often isn't. It's often poorly implemented, inefficiently implemented, and problematic for application code. So we'll look at some more examples later on in this talk of how you can have efficient profiling and good profiling, and how it's done kind of the bad way or the wrong way, as it often is. Now here's an example of where instrumentation could be blind in comparison to profiling in a real-world example. So this is an anonymized, abstracted version of a problem that one of our customers had. They had a slow endpoint, HTTP endpoint, every 5 seconds or so, and they would pretty much have like a unresponsive endpoint for a couple of seconds. On a servlet request, when they looked at their instrumentation-based APM tool that they had set up there, it was instrumenting the servlet request. So it would not show any kind of pause. Their monitoring tool was saying, hey, look, guys, everything is okay here, everything's cool. And then when they talk to their customers, they say, It's really not that cool. It's really quite slow. Now, the cause of this problem was that Tomcat was expiring its resources cache every few seconds, and on the load of that resources cache, the reload, it would scan the entire class path looking for different libraries and jars and trying to understand what was going on there, so it needed to reload. Now, this was really, really obvious when you attach a profiler. You're like, why is Tomcat doing all the work? Why is it the dominant consumer of your CPU? But you would never have got here with an instrumentation approach unless you guessed that this was an issue. Most instrumentation-based systems wouldn't monitor for this kind of thing. The other problem that we have with instrumentation is, as I say, the overhead. The more detailed, the more actionable, the more insightful the instrumentation is, the more instrumentation you actually need to put into your system in terms of lines of code, the more bloated and slow it becomes. You've got a nice, efficient plane flying through the air, and you're weighing it down with this big blob of instrumentation code sometimes. It can become the performance problem rather than a tool to help you find the solutions to the performance problem. Surely there's a better way. That's what we really want. We don't just want metrics. Metrics are super useful, super insightful, but they're often not that actionable. Diagnostics and diagnosis are two different things. Diagnostics is a way that you can measure a particular part of the system, a test that you can apply to give you some information, and a diagnosis is the result of your entire diagnostic process. Different things like metrics, profiling, instrumentation, these are all diagnostics. They aren't how you get a diagnosis. You get a diagnosis by putting these things together or having a tool that helps you put them together. So the question is, how can we use production profiling, continuous profiling, combined with metrics in order to understand and gain insight into the systems in front of us? So the solution to that is continuous profiling. Now, a lot of people might use profilers in development. They might use profilers in an ad hoc fashion. That isn't really continuous profiling. Continuous profiling is having always-on profiling in your production environment and storing and aggregating the results of that. How would we use a continuous profiler if we had one? Well, firstly, you've had a performance problem. You narrowed it down to a time period or some machines, and you want to query over that time period. You want to select a type of profile, CPU time, Wallclock time. We'll look at the distinction between those two in a sec. Or it might be memory-based profiling, allocation rate profiling. We're going to view the results of that profiling to see what the dominant consumer for resource is, then fix that bottleneck and kind of iterate and repeat. So this is an iterative process where we're trying to find the bottleneck by fixing the biggest problem and then, or the biggest problem that we see with our profiler, and then repeating until we've solved the overall problem. Now, I mentioned CPU time and Wallclock time as two different types of time that we have within our profilers. What's the distinction between those two things? Well, CPU time is like the time when you've got an execution, when you've got code actually executing on the CPU, so actually retiring instructions, actually doing work. And Wallclock time is the beginning of an operation to the end of the operation. Those two times can differ for a variety of reasons. Work can sit there queuing, waiting to be scheduled if you've got, say, lots and lots of threads and not many cores. You can be sitting there waiting behind a hot lock for another thread to finish its work. Lots of different things here. Now, I'm a real coffee fiend, I'm a real coffee addict. I'm drinking a coffee whilst we are recording this talk, even. And I love coffee analogies. So here's a coffee analogy to explain the distinction here. If you go to any good coffee shop, or even a Starbucks, you'll find that there's a big queue of people outside waiting to have their coffee. And the Wallclock time is like the time from you entering the first stage of that queue to you getting your delicious cup of coffee at the end. And the CPU time is a bit like just the time taken to make the coffee and collect payment, the time when you've actually got baristas working on your coffee. Now, why does that matter? Well, in order to understand a wide range of performance problems, you need both CPU time and wall clock time profiling data, but you need both of those things for different problems. So CPU time data will let you diagnose computation expensive hotspots. They'll let you diagnose inefficient algorithms. They'll also tell you about code that shouldn't be executing but is. Remember earlier in the talk we gave that example of the Tomcat reload? That's something that CPU time profiling will help you see. That's code that you don't think should be running but is. Other classic cases of that are loads of time spent in logging, loads of time spent by other APM tools, loads of time spent throwing and catching exceptions, which you'd be surprised at how many production systems sort of in their development have ended up throwing an exception and catching an exception, and that's taking up time in their CPU profile. Wallclock is a different puppy altogether. Wallclock lets you diagnose blocking that stops the CPU usage. So could be blocking on lock contentions within your system. It could be blocking on locks within libraries. It could be blocking on doing external I/O or waiting for a remote service or a remote database to return a response. All sorts of things. Waiting for a connection from your connection pool could look like a blocking problem that you would see with wall clock time profiling. Then we've got our profiling hotspots view. So how do we visualize different profiling data once we've actually measured it? How do we see the results of our profiling? Well, hotspots are the kind of simplest view of flat profiles, another way you can see this referred to, and that's literally just a list of methods ordered by the amount of time or the amount of the resource that they are consuming. So good hotspot profile views will tell you also things like the line numbers within a method. So that line number information can be super useful, for example, if you've got a few very large methods within your application. One of your colleagues has come along and written some 300-line monstrosities and you don't really know what's going on in them, and they're the performance hotspot. You don't want to just be told, oh, it's in this big method. You want to be told it's this line number in particular. Then another thing that good profiling hotspots visualizations can do is also give you the stack traces for those methods. What was the causal route to that method? It wasn't just, zip file.getEntry. It was zip file.getEntry when doing what? What's the thing that led us there? What's the vector back into application code? Flamegraphs are another cool visualization, a more modern visualization, innovated by Brendan Gregg from Netflix. Flamegraphs are a visualization of profiling data where each box in your flame graph corresponds to a method within the application. And methods, you can get flame graphs that go top down or bottom up. So this is a top down visualization, but they're basically the same but just mirrored vertically. The top down visualization with flame graphs, every method lower down in the graph is being called by its parent. So the top method in a Java flame graph will nearly always be java-lang thread.run, and then you'll have other methods within that. Finally, going down to your application code and often back into library code again. Now, profiling flame graphs also show you how much time they use. The way they show you how much time is through the width of the box. The width of the box is the time taken by a method or any of its children to perform a certain task, within the profile. And the interesting bit is when you see a method that is wide and has only narrow children beneath it. That's when you have a method with lots of self-time, when you see the method narrow down a lot. Okay? And the self-time methods are often the hotspots, other things to narrow in on. Flame graphs are really good because they provide you profiling data in context. You see what was the relationships between methods. It wasn't just a method that was hot in general, it was a method that was hot because it was being called by something. So we mentioned earlier that one of the big reasons that people don't use profiling continuously, profiling in production, is the overhead. So in order to understand how we can do low overhead profiling, we need to understand how profilers work. Firstly, there were instrumenting profilers. Instrumenting profilers are super old school, the simplest, oldest form of profiling data that we can see. Instrumenting profilers add instructions to collect timings, like the kind of beginning and end of method I talked about earlier. Things like the JVisualVM profiler does this. Now, instrumenting profilers tend to be quite inaccurate. They're inaccurate because they modify the behavior of the program under test. So the reason that is that the instruction timing instructions tend to be pretty constant in terms of time, and they happen at the beginning and end of methods. And certain methods are very small and very quick, and certain methods are very big and take a long period of time. So what you're doing when you're instrumenting a method like this is you're making your sort of quick methods take much longer in proportion, in terms of the proportion of their time, compared to the longer method, and that's introducing a bias into your profiling results between the sort of time taken to run individual method calls. Now, instrumenting profilers are, as well as being inaccurate, also have very high overhead, often 2 times slower, sometimes even more. Depends on your application, depends on how they've written their instrumentation code, but either way, instrumenting profilers, yeah, very high overhead no matter how smart you are, really. So a better approach in terms of overhead is sampling or statistical profilers. These can also be made more accurate as well, or at least less biased, should we say, to particular behaviors in a program. The way sampling and statistical profilers work is periodically you interrupt the program, you collect a stack trace of the program at that point in time. So in this visualization on this slide, your program methods are the white boxes. So we've got a web server thread.run, controller.doSomething, all up to a new person. And the green vertical lines are points in time in which the profiler captures the stack trace of the program that's being executed and gets that data back. Once you've got those stack traces, you can build up an aggregate picture of the profiling data. The more frequently you see a method in a statistical profiler, the hotter it is as a hotspot. You can't tell from a statistical profiler exactly what the number of milliseconds is that a method was executing as such, but you can tell the proportion of the overall time. And that's kind of what you want, really, because you want to know where's the bottleneck, what's the thing I should be looking at fixing, what's the problem. And that will be something that you can infer from the proportion of time spent in those different methods. Now, not all sampling profilers are the same. And in order to understand what makes a good sampling profiler versus a bad sampling profiler, we need to understand a little bit of background information. Most sampling profilers on the JVM use a JVMTI method called getAllStackTraces, and that requires a Safepoint. In fact, under old versions of the JVM, it requires n+1 Safepoints, where n is the number of threads in your application. On modern JDKs, they have thread local Safepoints as well, but you still require 1 global Safepoint and then n thread local Safepoints for each thread. Safepoints are a general mechanism inside the JVM for bringing threads to a halt. They're used by lots of different things. They're used for things like stop the wheel garbage collection pauses. They are used for things like on-stack code replacement. They're used for going from thin locks to fat locks. The JVM dynamically optimizes different lock implementations because certain locks are heavily contended and certain locks are not very heavily contended, and different lock implementations are optimal in different situations. But the key point is, the way Safepoints work is they poll, i.e. read a value out of a known memory location. And this is a page of memory that you have sitting that the JVM owns. And what the JVM does is it triggers something that's a bit like a segfault. So it puts a protection handler around that page of memory. And when the application thread tries to read a value out of that page of memory, it gets the operating system interrupts that read and starts running the handler, and that's how the JVM bootstraps back into JVM code when it wants to suspend threads. Very good mechanism for garbage collection if you need to do a stop the world pause. But what's the impact on Safepoints? Well, because those Safepoint polls are bits of instrumentation, and instrumentation has overhead, even a read of a 0 value. Safepoint polls only happen at certain places in your code, at the beginning and end of every method. That's what these kind of light blue turquoisey dots are within the methods. They're the Safepoint poll points. And that means, as opposed to you having, if you've got a Safepoint based profiler, then you will only see the Safepoint polls. You'll only see your stack traces at the points when the Safepoint happens. That's where these red lines occur on the graph. Your Safepoint poll has been reattributed to a wrong bit of the code, and in one of our cases, two polls have been converted into one. So view.print.html in this code is being underestimated by 50% in order to get its accurate profiling data, its accurate, the accurate amount of time that is taken in the system. Now, Safepoints also interact with other JDK optimizations. So inlining is a very common optimization within the JDK. So inlining is where you take the body of a method and inline it, or copy that code into the method that calls it. And that enables a lot of other optimization opportunities, and it removes some of the method call overhead. Part of the method call overhead that it removes is the Safepoint poll itself. They get written away from the application. So here's an example where our purple methods in the graph, new person, repo.read person, view print HTML, and the two with question marks, they're all inlined into their parent methods. And as a result, the time that should be attributed to those methods, where we should have those green lines, actually gets reattributed through the red line to the one dot at the end. It completely skews the profiling data. Often you have small, well-written code in the JDK, and inlining can make that fast, but it can also mean that Safepoint bias profilers just give you the wrong answer. Loads of time for these kind of systems. This isn't the only way that optimizations interact with Safepoint bias. There are Safepoints within the back edge of a loop, and those Safepoint polls can get optimized out from those loops if your loop is a counted loop. So that means it's something of the form for int I equals 0, I less than I plus plus. Okay. There are options on certain modern JDKs to avoid that optimization from happening, but it does in most cases. Then there's the time to Safepoint problem with Safepoint polls. Now, this is less of an issue from Java 11 onwards, where thread local Safepoints have been added, but on older JDKs, it's an issue, and on 11, they still do a Safepoint in order to get the number of threads that are available and get all stack traces. There is still a Safepoint related issue. In the time to Safepoint issue, what's happening is you're basically waiting for all of your threads to come to a halt before you do your VM operation. So the VM operation here is actually collecting the stack trace, but that VM operation refers to anything that is happening under a Safepoint here. So it could be a garbage collection, pause, or all sorts of things. If you've got one thread that takes ages to reach a Safepoint, maybe it's doing one of those hot counted loops where the Safepoint polls have been optimized away. Maybe it's running some native code like a JNI or something like that, and it won't get to a Safepoint yet. Those things hold up Safepoints from happening. And your other threads are just sitting there paused. They're not doing anything. You're reducing the throughput of your system. You're reducing the performance of your system. You're potentially introducing jitter and latency into your system. These are all negative consequences of doing Safepoints lots. It's okay if you can do a GCA event anyway, but if you're trying to do this loads and loads and loads in order to get accurate sample-based profiling data, you are going to have a bad time. You are going to slow the system down. There's a good way of doing sampling-based profiling, statistical profiling in Java, and we're going to talk about that now. So get all stack traces. You don't want to do that for a production profiling system, but you still need to solve two problems. Problem one, interrupting the application, so saying, look, stop now, we're going to measure what's going on, and point two, actually sampling the resource of interest, so getting the stack trace. You can interrupt the system with operating system signals. There's even a special signal called SIGPROF designed specifically for profiling, delivered to a handler on one thread, round robins different threads, or randomly sends it to a thread. Very, very lightweight, very, very low overhead, fantastic. Then you sample your resource of interest. So there's a method within JDK called Async-call-trace to sample the stack. And then we can examine JVM internals to find other resources and other points of interest. Okay, so that's how advanced statistical profiling works in Java. It's not an approach that's used by many existing profilers. Most desktop commercial profilers don't use it. JVisual VM doesn't use it. It can give you very, very low overheads for very reasonable sampling rates. So it can give you less than 1% overhead, we found with our implementation. Different implementations might have different overheads, but that's what we target. There are different low overhead ad hoc production profilers. So these are just projects you can download, run in a desktop environment that are very low overhead. Async-profiler, honest-profiler. Perf doesn't use async get call trace. It uses the perf stuff in order to understand where the methods what methods are actually being called inside the stack trace. There's Java Flight Recorder or Mission Control. That's very cool, and Solaris Studio as well. But these are all ad hoc production profilers. And in practice, people get put off as much by practical issues as they are by technical ones. So the problem with ad hoc production profiler is it requires access to production, which not every developer has. And even if you do have it, the kind of fiddly manual process of trying to hook up a profiler to a JVM process that might be in the middle of dying or crashing, it can be problematic. And often it's very difficult to attach to certain systems or to use JVM attach methods to systems which are under performance impact. It's manual work, it's ad hoc work, it's hard to automate. You don't get support contracts from the open source profilers necessarily either, so it can often be risky in people's minds to attach these to production systems. What if we profile all the time? So what benefits do we get from profiling continuously? Well, firstly, we don't have to worry about attaching our profiler to a production system in the middle of an incident. But we also get loads of other benefits as well. We get historical data, post hoc incident analysis. You had an outage at midnight. What caused it? What did the profiling data say? You don't have to worry about having to have someone awake to hook up a manual profiler to do that. Enables correlation with the data and metrics. You can timestamp things. You can look at like, hey, my metric said the CPU time increased yesterday. What was the profiling? What does our profiler tell us about what happened then? Performance regression analysis. You've released a new version. The CPU usage has increased. Why did that happen? The profiler will tell you. Putting samples in context. Ad hoc profiling is very difficult to understand, like machine-related systematic causes of profiling data. Things like environment parameters, application versions, stuff like that. Once you've got continuous profiling, your profiling tool can just gather that from the local system and tell you what's going on there. Ad hoc profiling doesn't do that. Google have a really good tool and a really interesting paper they've published on Google-wide profiling where they've done continuous profiling data. I'd link it there. If you're interested, go have a read of this after the talk. It's been really, really cool to see what they've done there. Very interesting. So how are we going to do production profiling in practice? Well, we have our JVM agents that profile the system. They send that data back to an aggregation service, and we can see the results of that data on a kind of web-based report that anyone in your team can have access to at the end. Now, this process of aggregating the profiling data is really useful. It means you can see differences in profiling data between different JVM agents. It means you can have a central source of that data for historical data, for querying, all sorts of stuff. Traditional profiling tools just don't really support that very effectively. So in summary, it's possible to profile in production with low overhead. You can do it. We can all do it. You can overcome the practical issues by profiling all the time or continuous profiling, and you gain new capabilities by profiling all the time. There's stuff that would be difficult or impossible to do before that you can do now. Okay, let's quickly wrap up and draw some conclusions. Firstly, thanks to Brendan Gregg and Andre Pangin, Jeremy Manson, Johannes Rudolf Nitzen, and the mission control teams. They've all done great work on various profiling implementations in the JVM and visualizations and all sorts of stuff. It's fantastic to see the work that people have done in the field for this kind of thing. In this talk, we talked about why performance matters, why understanding your unknown unknowns was the real key to solving performance problems, the distinction between development and production environments, how just looking at things like metrics on their own can be difficult to find actionable solutions, but instrumentation, which is what most people jump to, often has high overhead, but continuous profiling can be low overhead, hypothesis free, and really insightful and really useful for solving performance problems. We need an attitude shift on profiling and monitoring, in my opinion. And what that means is moving to being systematic, not ad hoc, about performance problems. Having a clear-cut methodology and diagnostic approach that will work for different systems that helps you solve problems rapidly and efficiently. And that is something that we're supportive of here, and we'd really like to see happen more of. Being proactive, not reactive. Proactive here doesn't mean doing premature performance optimization. Proactive here means putting the right things in place to measure your system and observe your system in production and understand what is going on there. Rather than reactive, where you're just like, oh my goodness, we're having a problem, we're having an outage, how do we fix this now? And in order to achieve that goal, you have to be continuous. You have to look at what is going on, measure that historical data, put it up head to head with that data and be systematic and continuous about it. If you've got one takeaway from this talk, it is please do production profiling all the time. You will love it. Your team will benefit. Fantastic. And as I said, I run a company called Opsian that helps organizations do this. Feel free to come and talk to me after the talk or hit me up on Twitter. I'm at Richard Warburton on Twitter. Some of our customers have been really happy with Opsian as a tool for doing production profiling, but you don't have to use Opsian. The key point is to do production profiling. You'll find it really useful. If anyone has any questions, I'm happy to take them now.
Awesome. Thank you so much, Richard, for such a thorough explanation and representation of the importance of profiling, ways to do it efficiently, challenges. It's really great. I wish we just had this talk, probably one of the first ones, to introduce some of the things that were discussed later on. So Dmitry already has a question for you. Richard, is there a particular profiler suitable for continuous profiling? Is the Async-profiler suitable?
So as I mentioned in the talk, our company Opsian does a continuous profiler as a service tool. So obviously we think that's pretty suitable for solving that kind of problems. You can get a free trial on our website for 14 days on just opsian.com. The question also mentioned Async-profiler. I think Async-profiler is an accurate, low overhead, open source profiler. So I think you can use it in production without having too much overhead on your system. The problem is if you use something like Async-profiler or Honest Profiler or Java Mission Control's flight recorder system, that doesn't solve the kind of back-end data collection and querying aspects of continuous profiling. So it's suitable for implementing something like Ad-Hoc production profiling, where it's on in production, but you have to sort of deal with a particular server and do a lot of handheld work in order to get that data, but it doesn't give you kind of the aggregation and querying and all the stuff that you need to make continuous profiling super effective and super efficient as a development approach for a whole team of developers.
Yeah, that makes sense. I actually have a continuation, I guess, of this question. Dmitry has. Can you not use with some hand wiring async profiling to continuously do profiling while having manual data collection?
Sorry, what does he say there? Can you not
use with some hand wiring async profiling to continuously do profiling while having manual data collection, i.e. data collection of our own?
So you can definitely use Async-profiler for data collection. The problem is that if you take a kind of approach of manual data collection, it doesn't scale out to a wide number of servers very effectively. You need to kind of connect up to those different servers. It doesn't really work very effectively for historical data comparisons. So suppose you do a new release with something like Opsyn, you can just look at the current version of your profiling data and the previous release of your profiling data. With manual data collection, you wouldn't have that historical data sort of stored, queryable, comparable. You also, in certain organizations, have difficulty getting manual access to production. So there's several different reasons for this. A lot of institutions like banks have regulatory requirements around institutional Chinese walls. So like people who write development code can't necessarily be the operators of that production system. And a lot of organizations just discourage manual access to production systems because it's a bit of an anti-pattern from a DevOps point of view, right? It doesn't scale out to a wide number of servers. It kind of encourages a lot of manual work. So I would say something like Async-profiler is basically like you're going to end up building a whole bunch of tools around it in order to make that work. But it will definitely gather the data for you.
Yeah, actually, that's, I think, some of the points that Fernando has mentioned during his presentation about AWS Code Guru Profiler, because it's like for small deployments, it's fairly feasible to do these kind of ad hoc profilings. But at huge scale, like we also have the same challenges at Facebook, like it just doesn't work, like it's just impossible. Which brings me to another question. I actually had a question. So we actually operate at such a scale that there are so many servers that just the collection is a challenge on its own because there is just so much data. And so we are experimenting with all sorts of adaptive techniques where we can detect certain conditions where maybe a little bit more frequent sampling would be more appropriate, just to capture more context, so that whenever you have a suspicion that your service operates under some strange conditions, like it basically exhibits some weird behavior, then you can even increase your sampling rate, or maybe start capturing even a little bit more data. So for example, maybe in addition to CPU sampling, you also start doing memory sampling or some other capturing some other data just for that specific instance, so that overall, in general, you don't overwhelm your system with like a very unuseful data, but at the same time, for the incidents, you actually have extra context to work with. Arun has a question. In your experience, do you see sampling, e.g. one from Opsyn or JFR profiling as sufficient coverage? Does it really cover off the coverage gap with the old sampling profilers, or are there still edges around it? For example, how many quick methods not being caught but taking long in total?
Yeah, that's a good question. So there are different types of sampling profilers, and they catch different things. At Opsyn, we've got a CPU time-based profiler, we've got a Wallclock time-based profiler, we've also do allocation profiling as well. So CPU time-based profiling will capture what's actually executing on CPU, and that will cover things like small methods that get caught a lot and add up to a lot of time in total. Wallclock time profiling similarly is about basically capturing time where you're kind of executing on threads and blocking. So that will capture things that are taking up time where they might be off CPU or blocked on a lock or waiting on a remote service call or a database or things like that. I don't think that there are particular problems with those approaches of not capturing small methods, as he mentioned. There can be problems with traditional get all stack traces based profilers on the JVM. I kind of mentioned that in the talk, where basically they rely on Safepoints to be the only point to which they capture stack traces, and then when the methods get inlined into larger methods, those Safepoints disappear, and then the methods disappear from your profiling data. We don't suffer from that kind of problem. the async profiler shouldn't suffer for that kind of problem. With respect to flight recorder, it depends upon what profiling events you use, because they have different profiling events. The flight recorder that ships with most JDK releases doesn't do proper Wallclock time or CPU time profiling. It sort of has this weird mode where it picks a certain number of threads and then samples them differently. So it has a sort of, it's hard to describe off the top of your head, but it has a different kind of bias to it. So you may use flight recorder and find that certain methods don't get picked up, but I don't think that should be a problem with Opsian or something like Async-profiler. And I think the flight recorder guys are in the process of adding Wallclock and proper CPU time profiling events to kind of cover off that weakness or lack of visibility problem at the moment. I just don't know what release those will be eventually in.
We are a little bit behind the schedule, but the last question, and he's also asking, Arun is also asking, how is the continuous memory profiling handled? But I believe you mentioned that you don't do it, right?
So in Opsian, we do continuous we do allocation rate profile. We do allocation profiling. So we capture allocations, and we also capture stack traces periodically on allocations. The async profiler does that, and flight recorder will also do allocation profiling, but the open source honest profiler projects and kind of perf-based profilers don't do allocation profiling. The way that works in things like async profiler and mission control is basically looking at when allocations happen on the JVM, they happen in T-labs, and then periodically those so that's a thread local allocation buffer. Periodically, those T-labs get transferred over into your main kind of young generational heap, and then eventually promoted up to tenured generations. So with T-labs, there's a point at which those T-lab switches happen, and they just sample allocation events when those T-lab switches happen, as that's a kind of, so it's a sampled allocation profiling rate, but in practice, like a lot of sampling based approaches, when you run for a while, you capture the appropriate data points, and it's a realistic picture of what the actual main drivers of allocation are. So it's still a pretty reliable and a pretty accurate technique.
Awesome. Thank you so much, Richard. We are, like, as I mentioned, a little bit behind the schedule, but I really appreciate your answers. And fortunately, we're going to have you for the panel discussion. So I hope we can continue the discussion around challenges in profiling. So we'll see you in about an hour. But for now, we are going to take a small 1-minute break before we continue with the last talk of the day, which is going to transition a little bit to the reliability aspects of using instrumentation and profiling. So I'll see you in a minute. Thank you so much.
Thanks. Bye.